Hi and welcome. In this demo we're going to be simulating the legs of this robot spider using dynamic joint chains. Now to begin with, let's create an empty game object here. I'm going to call it spider leg dynamics, and I'm going to add a component called a dynamic chain. Now in this component I'm going to specify that we have 8 sources because the spider has 8 legs. Let's grab the roots of these legs and drag them into the slots of our sources. Bear with me a second. Alright, so with that done, let's generate particles. So if we scroll down to the bottom of the dynamic chain, under chain processing, there's a button called process chain. We can press that to generate the particles. First, I'm going to take the particle radius here and set it to 0.05 instead of 0.5 because that's too big. That's going to be the size of the radius of each particle. I'm going to press process chain. If you don't do this step, then it'll automatically be generated when you play in play mode. There we go. And as you can see, it takes each of these root elements and adds a particle to every one of its children in the hierarchy. There are, however, some particles we might want to skip, i.e. these two. I just want this particle and that particle to be simulated. And to skip it, we can make use of the exclude tag. Now, if I select this particle, which I want to not include, there's an inspector section that gets revealed. I'm going to press go to game objects. You'll see this game object. I've already preset the tag to exclude from dynamics. You can create this tag here by pressing add tag and creating one, or using an existing one you've got in your project. I called this one exclude from dynamics, and everything else is untagged, which I do want to include. Now to apply that, I'm going to go in here and specify exclude from dynamics as the tag. And then I'm going to press process chain. And as you can see, it skips those points which have that tag and ignores them when generating the particles. Now I've got only what I actually want. Perfect. Okay, now with that done, let's go into our dynamic settings. First of all, initialization from, I've set it to last frame continuous. If we set that to static pose, it simply means that at the beginning of each frame, it resets the orientations to the rotations we've got in the static pose here, and then it solves towards its targets from those orientations for more consistency. I'm going to use last frame continuous because we wish to use joint chains in the system, and it's just better as far as reaching the targets while not getting stuck in local minima, by using the last frame's orientations. Number of iterations, I'm leaving it to the default of 3. That's just the number of iterations of distance constraints to apply per frame. The higher the value, the better the results, the more stable. Force strength, so the dynamic setting, force strength is just a multiplier for the forces that are applied, i.e. based on the gravity. Damping, I'm going to set to 1. Drag represents things like air resistance or water resistance as you're traveling against them. I'm keep it at 0. Spring strength, let's set that to 2 for now, and so on and so forth. Start weight and end weight are simply the spring strength, the weight at the roots versus the weight at the end, i.e. the end position versus the roots, and it's applied as a gradient. I'm keeping it 1 so it's constant throughout. We've got this thing called prevent stretch. I've set it to true. Well, it is true by default. It simply means don't allow the bone lengths to stretch whatsoever. Which we do want in this case because it's a robotic kind of system. It's not something like a tentacle or something stretchy, which is organic, or a rubber band. So with that done, okay, let's set a gravity of, I'm going to set minus 35 in the y-axis for now, and let's play. Let's see what happens. One more thing. I'm going to remove use limits because I want to show this off without joint limits. And as you can see, gravity is taking effect. However, because we're not using joint limits, our particle system is behaving, or the legs are behaving like pieces of string. which we don't want. So this is cool in some cases, but not in this particular case. While we're at it, I'm going to demonstrate stretch. So if I remove prevent stretch, then the stretchiness is the value of stretch which I want to move towards. So we could increase it by 10%. It's going to always try to stretch it by 10%. The stiffness it represents how stiff it is going towards that target stretch. The higher it is, the more it'll stay fixed to that stretch. The lower, the more it'll oscillate as it moves towards that stretch. So with the low value, you see that there's this, stretchy, bouncy effect because the stiffness is quite low. It's more like a rubber band kind of effect. Now, obviously, we don't want to use any stretch at all. So I'm going to press prevent stretch once again. And we're only going to be dealing with rotations. Now, the first thing we want to do is use joint limits, after all, because this is, a mechanical kind of articulated joints and all that kind of stuff. So I'm going to use joint limits. Now, we've already authored joint limits in advance. If I take one of these particles, if I press go to game object, you'll see that this game object, I've pre-authored a dynamic joint limit hinge, which is a hinge in a single axis of rotation of freedom. I've already authored this beforehand. I've set the angle limit to 180, but it just means that we can only, rotate within this axis of rotation and no other axis. If I take the parent, you'll see we've got a swing twist limit. Now on the limit angle, it's 0, meaning the swing range is 0, but also the twist range is 0. So essentially, we're completely clamping the rotation on the shoulder joint here. Now, to demonstrate what would happen if I increase that limit angle, especially under gravity, to go downwards, if I increase that range, you'll see that now we've increased the range of motion, and gravity can actually bring that joint downwards. I'm going to restore it. Now, what I'm going to do is play around with the joint limit here. So if I change that limit angle, you'll see as the bounds reach a certain point, and I could change the offset as well, then the particles react with it while still going through the dynamic simulation and having forces and gravity apply, and while preserving that weight shift and change of momentum, but at the same time interacting with those boundaries or the joint limits, as you could see. So that's the strength of this tool. Having a structured particle system, which is simple and quick to set up and that doesn't go through a physics system at all whatsoever. So with that demo complete, let's restore, the joint angle limits and then take this further. Okay, so now this is basically simulating with joint limits. As you can see, no longer like a piece of string. They're all moving within the correct hinges and so on. Now I'm going to demonstrate the addition of colliders. So we support dynamic colliders or native colliders. Dynamic colliders are bespoke ones which come with the package, such as sphere or capsule or cone colliders, which you can add to empty game objects as components. However, we also support native colliders, which is more straightforward in most cases, so we're going to use that. Let's add 2. In this case, I'm going to add this capsule I've got in this scene. So I'm going to drag that into our colliders. Also, I've got a sphere collider representing the head, so that I don't want the particles colliding with the head. It's under the maintenance orb main. I'm going to add that as well. With the colliders added, whenever I move this capsule, let's say, then you'll see that our particles, based on their radii, are going to interact. And we're going to have collision interaction while also running everything else, i.e. the joint limits and the dynamics will be running in parallel. Everything will be solved at once, as you could see. There you go. And you'll notice because I've got, the shoulders are completely clamped, we can't solve for twist at all. What that also means is if I rotate the system as such, then because we don't have any range for twist, we can't bring the legs of this robot downwards. However, if I go into my dynamic system and I enable, or rather, if I select my the shoulders of the legs or the roots of the legs and I increase that twist limit, what you're going to notice is because of that increased range of motion for twist, finally I can actually move apply twist to solve for the dynamics as well. There you go, and you'll see that, we could twist too and also bring those down. And likewise, if I move the colliders in, you'll see even during collision, because I can twist, I can also, solve for twist while avoiding that collider. This is an additional powerful feature where we also support twist in the dynamics with an additional step. We've got under limits of our dynamic chain component, we've got this field called solve twist dynamics. It's on by default. I keep that on. There's also a max twist rate, which is 45 for now, degrees per second, if I remember correctly. So yeah, we could keep that on, and yeah, we could solve for twist as well in the dynamic step based on those joint limits. All right, so with that said and done, let's go back to where we were. I'm going to introduce the concept of mass inertia. So if I remove, the gravity field, I'm going to now instead add a force of inertia. Let's set a value of 5 for now. And what that's going to do is it takes the initial pose or configuration and it's going to apply forces to get our particles and joints to move towards their initial positions and orientations relative to their parent spaces. And that's what it does essentially. The higher the value, the stronger the effect. So I removed gravity, but it can work in conjunction with other things such as gravity. And now I've got inertia. And as you can see, it's still running through the dynamics filter and running simulations. I can even take this capsule and run it through it. And you'll see it'll still interact with our colliders as well. There you go. What I also want to do is I'm going to copy this component now. I'm going to exit play mode. I'm going to paste the values as they were, but while not in play mode to preserve what we did. I'm going to add a new component called dynamic forces. So this dynamic forces component, sorry, my bad. Let me do that again. Yeah. So we can add external forces to be layered on top of the gravity. So I'm going to create a new force. We could specify we could layer these forces, but in this case, I'll just create one. The target space, world space, target transform space. You could fill this field here and it'll operate in the local space of that game object. We can also set it to per particle space in the local space of each particle. I'm going to choose root particle space, which is in the space of the root particle of each branch, i.e. of the roots of the legs, basically. I'm going to set the progression mode to sine wave instead of constant or Perlin noise. Let's set the force to be x value of 1, so in the local x-axis, which I think is outwards in the case of these legs. Let's set an amplitude of 5, a frequency of 7, and let's see what happens. We've got forces strength. We could set it to 0. You can change it here to modulate it. I'll keep it at 1. So if I play this now, you're going to see that we've got this sine wave force applying on each leg, but in their own local space based on the root particle space. It's too uniform, but there is something called time offset per branch. I'm going to set that to 1. And what that does is it just creates an offset for each branch randomly. So now there's like a 1 second offset, for each branch. There we go. That's the forces system. You could layer a number of these forces in different spaces for different effects. But this was for demonstration purposes. I'm going to set that force strength to 0. Let's set the inertia to 0 and restore gravity. There we go. We're running gravity once again. I think, yeah, because we're in play mode, we've lost that twist limit. So I'm going to set the twist limits to 180 once again. Now with the 180 twist limit, even if I rotate this way, you'll notice that because we've got that sphere collider as well, the legs won't simply go through the head, but they'll slide around the head. Okay, so the last thing I wish to demonstrate is inverse kinematics. So if I'm to select a particle, i.e. the end joint of this particular leg, at the top we can reveal this inspector section, which gets revealed for that particular particle, where we could set like particle specific data. Now the target constraint here is set to none. However, I could set it to a position constraint or a target force, so that we apply a specific force only on that one particle towards a target. In this case, I want to demonstrate inverse kinematics, so I'm going to press inverse kinematics. Now, the target is set to the 0 space by default, but there's also a transform. I've already pre-authored a game object, which is empty, called robot limb target. I'm going to drag that into the target transform. It exists in space somewhere, and as you could see, by doing so, that particle is going to be moving with inverse kinematics towards that target. So I'm going to move that target around, and as you could see, we've got inverse kinematics running, but at the same time, we're still running through that dynamic simulation, meaning the gravity is still applying. You still get that secondary motion from the dynamics with, the force strength and the spring strength and all that kind of stuff. So all of this is playing in parallel, and yet we've got a full inverse kinematics system running in a layered way as well. And the beauty of all this is we don't have to go through a physics system or engine whatsoever. It's all simple, it's performance, and that's the winner here, just based on these components that we add. This is all driven by this one component and some particle settings. So yeah, with that said, I could select the parent particle and then set that to inverse kinematics, and it'll overtake what the child was doing. And likewise, I can move the inverse kinematics point, except for in this case, the child will keep doing what it was doing before, like, simulating based on gravity, but the inverse kinematic applies to that parent particle. And because we've got twist range, we can actually, from the root level, we could solve towards it. There we go. I'm going to press none once again. And the very last thing I want to demonstrate is the concept of custom distance constraints. So if I take this particle here, let's say, in its inspector section, there's something called custom distance constraints, and I can press this author new constraint button. And once I do, we're going to be in the selection mode. It says select a particle to constrain with. Let's select the neighbor on the neighboring branch. With that done, you can see we can visualize this constraint over here. And if I'm to look at that constraint, then there's a value. There's a type of fixed distance. Fixed distance will make it act like a bone length. So I could change that fixed distance. And as you can see, it's forcing my system. It's forcing the distance between the two to be fixed. So you could create a series of these to create like interesting structures. For now, let's remove the usage of limits, just to demonstrate this more well. I can also change that constraint to be of a different mode, i.e. minimum distance, which means that the distance can be greater in the simulation, but as soon as they get too close, they're projected out to that minimum distance. Likewise, maximum distance, which simply means that, they can maximum be a certain distance away from each other, but if they're more than that distance, then they get constrained towards each other. So as you can see here, because we're allowed to be closer, the particles go closer, but those are the actual bounds, that, the bounds of the red line on either side. I'm going to keep it on fixed distance, and then as you see, we can even move it, and that constraint is going to keep operating. To make it more interesting, let's add a constraint between these end particles. So let's say this one, and I'm going to set that to a low value. There we go. And now I've got this thing with a custom structure, but yet still running through, our dynamic system with these custom constraints. There you go. All right. So I'm going to, that's everything. Thank you for watching.